All right, so today we're going to be looking at our rest of the notes on gases and stoichiometry. And go ahead and jot down this part over here. And once you've written it down, I wanted to explain what this is. So you guys probably remember doing stoichiometry as as a unit just by itself. But in this unit, we're going to be bringing stoichiometry back by also throwing in some gases with it. So just remember back to the idea that reactions always are going to be happening in mole ratios. So the number of moles or the coefficients you actually have in your equation really matter. Number two is an important point for you guys to note because this is actually a shortcut, and this shortcut is only useful if it's at STP. So remember, if it's at 273 Kelvin or 0 degrees Celsius and 1 atmosphere of pressure, then you know that a mole of any gas is always going to have 22.42 liters of volume. Okay, so this is an important shortcut that you actually don't even have to memorize this too. You get this for the test, but you just need to know when you could use it. So I'll refer to, I think there's one problem that we're going to do today that's going to refer to this little shortcut. If a gas is not at STP, then we have to go back and use the ideal gas law to calculate the moles of reactant or volume of the product. So the ideal gas law, remember, is just our basic PV is equal to nRT. Okay. Now, the stoich that you guys are going to be doing with me today, it's going to have a few steps to it. So you have to take a look at stoichiometry itself, and then we're also going to be doing PV-nRT, or that little shortcut that I had you look at. So let's talk about this part first. So we know that, and actually I think there was a question on the Dalton's law worksheet that mentioned this. Whenever you guys have a chemical reaction and there's water in that reaction, some of the water could actually evaporate. And when the water evaporates, the water actually has its own pressure to it. So this part you guys really only need to make use of if they mention it in the problem. Sometimes it'll say like, oh, this chemical reaction happened and this is the pressure of the water vapor. So if they ever mention that water vapor, you always have to subtract it out from the actual pressure that's given. And you guys will see some examples of this, I think, when you do the GasStoich worksheet that you're going to be doing right after this. So don't worry about it if they don't mention the water vapor at all, but if it is given, you just subtract it out from the total pressure before you do your calculations. Now, if you're looking at GasStoich, the in switch out process, you guys might remember the roadmap that you had a long time ago when we were doing stoichiometry. And there's two parts to this. You could see how much you're going to be writing in. This is kind of a given, like, if you know this and you're trying to go to that, these are the two steps you're going to take. And the same thing is true on the bottom. So when you're given grams or moles of some sort of a compound, and then they want you to figure out the volume of B, these are the two steps in the order that you're going to take. So you're going to first of all go to stoich first, or you're going to do stoichiometry first, and then make sure you stop when you go to moles of B. Okay, so we're going to stop before we get into the molar mass. Once you have that, then you're going to use the moles of B that you just solved for in part one, and then we're going to use PivNert, okay? Or we could solve for volume using the shortcut. So remember, you could also use at STP, a mole of gas is equal to 22.42 liters. So if it's at STP, I could just solve by using a really simple ratio and not even putting it into the ideal gas law. That's a lot faster. And we'll do one of those as a sample. Now, you could also have another scenario where they give you the volume of A. They'll say, oh, we have like 18 liters of this particular gas. And then they want you to know how many grams or moles of some other compound you can make with it. So in this case scenario, I don't really want to use volume when I do stoichiometry. So I am going to use PivNert first, and then I'm going to go out and solve for the moles of A that I have. Okay, so once you have moles of A, then you could easily go through and do stoichiometry and then solve out for grams or moles or whatever they have. And this shortcut, the STP shortcut, you guys could use it right here, or you could use it in this step here too. So just remember it's step 2 or step 1 of either process. So let's go through and take a look at this problem together. It says, mercury can be made by the following reaction. And we have this mercury 2 oxide that's turning into mercury liquid and then oxygen gas over here. So it says what volume of oxygen gas can be produced. So you could see I set up my oxygen as my B here. And I'm starting off with 4.10 grams of mercury 2 oxide. So this is my A and this is my B right here. And this is a problem that's going to be done at STP, which will be nice for us. So let's go ahead and set this up. Because if you look at this, I'm starting off with grams of A. I know that I'm going to start with this setup right here. So when given grams or moles of A, and I'm going to the volume of B, see how they wanted you to solve for the volume of oxygen gas? So I am going to use these two steps over here. So step 1 says to do stoichiometry first and go to the moles of B. So let's do that. I'm going to do my stoich down here. So I have my, oh, and I hope I have enough room. I might have to start working on this edge of the corner. So we have here's part 1. I have 4.10 grams of mercury oxide, HgO. Okay, and we're going to use stoichiometry, and I don't want grams of this. Our goal is to go to moles of B, so I'm going to try to go to moles of O2. So remember how stoich works? We're basically using dimensional analysis. So I know I want to get rid of grams of HgO, and then I could convert this to 1 mole of HgO. Okay. Down here, we're going to be putting in the molar mass of HgO. And our second step to the stoich is now we're going to be using mole ratios. I, again, want to get rid of moles of HgO, and now I'm going to switch this. I'm going to go to moles of O2. Okay, so this might recall, or this might require you to go back and find your stoich notes, but we're just using our roadmap to go from grams to moles. And from here, whenever you guys do the mole-to-mole switch, we're going to be making use of the coefficients we have right here. So I have 2 moles of the HgO, and I have 1 mole of O2 in my equation. And because I'm stopping at moles of B, I'm going to stop right here. So I'm going to stop right there, and I'm going to figure out how many moles of O2 I have. But let's go ahead and calculate out our molar mass for the mercury. So I have 200.59 plus an oxygen, so I'm going to add on a 16. So I have 216.59 down here, and I'm going to go through and punch this out on my calculator, and I have 4.10 times 1 times 1, and I'm going to divide it by parentheses 216.59 times 2 parentheses, and I'm not going to round off my answer yet because you guys want to round at the final part, so I'm just going to take it to a lot of digits here. But this is how many moles of O2 I have. Okay, so see how we did stoich to go from A over to B? Now the second step says use the moles of B that we just got. We just did that right here. And now we could either use PV-nRT, or we're going to use our shortcut, which says at STP, a mole of any gas is equal to 22.42 liters. So this is where it's actually really nice. Because it is at STP, they tell us in the problem right here, we can make use of the shortcut where 1 mole of any gas is equal to 22.42 liters of the gas. Okay, guys, if this were not at STP, then all I'm going to do is I'm going to use my PV-nRT equation. The moles are going to go in for the N. I would plug in my pressure, I plug in my R constant, I plug in my temperature, and then I'm going to be solving for the V. But this is just the easier way to do this because you're just using a quick ratio to get to your answer. So I have the answer still on my calculator. I'm going to multiply by 22.42. And how many sig figs do we need here? We started off with 1, 2, 3, so we're going to end with 3. 0.212 liters of O2 is our final answer for that. Okay, and just make sure you want to look at how all of our units are canceling out. The moles cancel and we end up with liters at the very end. Some people prefer to just tack this on into this original stoich setup too. That's totally fine. But just note that we're just making use of the shortcut. Now you see how this problem, they want you to calculate the volume of O2 gas again. Except this time, notice how we're not at STP. So this is great. Now that we have this, we could see an example of what you would do for step 2. So this part here was step 1. this part right here was step 2, where you guys used a little shortcut right there. But now let's try plugging it into PVNRT, because we know that we're not at STP anymore. So I'm gonna plug in my pressure. It's 740 torr, so I need to convert that. 740 divided by 760 to get it into ATM, and that gives me 0. I'm just going to use a lot of decimal places. 97368 ATM. The volume is the one that I'm solving for. The number of moles is what I have. Remember how we calculated that up here? So I'm going to put 0.0094649 moles. My R constant is the 0.0821, and the temperature is 400 degrees Celsius, so we'd have to tack on 273 to it, so we get 673 Kelvin. Okay, so we're going to go through, we're going to multiply this entire side, and then divide it by 0.97368 to get our volume here. So let's go ahead and do that. 0.0094649 times 0.0821 times 673, and then divided by 0.97368. And my volume comes out to, again, this time we have 2 sig figs because of the 740 right there. So we have 0.54 liters of O2 gas. So you could see how that worked out right there. And we're going to try this one more time just in case the steps didn't really make sense for you. And here you guys could see our balanced chemical equation. We have sodium bicarbonate with acid, and then it's making all these products over here. It says, calculate the mass of sodium hydrogen carbonate necessary. So we're looking for this right here. So remember that the thing that you're solving for is always your B. So this is the thing I'm going to look for. And we want to make 2.87 liters of carbon dioxide. The carbon dioxide is the thing I know, so that's my A right here. Okay, and look at what's given this time. You are not given grams this time, but you're given liters, and we know temp and pressure. So let's look back here to the 2 scenarios you guys could either get. When the volume of A is given, like we have right now, the 2.87 liters, and you have to go to grams or moles of B, then we have to go through and start with this scenario. So we have to use PivNert first, and we're going to solve for N, okay, or we could use the STP shortcut, but unfortunately we're not at STP, so we can't use it this time. And then we're going to go through and do stoich and then go to grams or moles of B. So let's start, go ahead and set this up. Step 1, I'm going to use PVNRT, and let's go ahead and plug in everything. It's at 2 ATM. The volume of my gas of carbon dioxide is 2.87 liters. The number of moles is what I'm going to be looking for, and the R constant is 0.0821, and the temperature is 25 plus 273, so we get 298 Kelvin. Okay, so let's solve for the N. We're going to multiply the 2 times 2.87 together, and then we're going to divide it by parentheses 0.0821 times 298, close my parentheses. And then I get 0.2, I'm going to take it to a few more decimal places, 23461 moles of, this is carbon dioxide. So that's what we know. Now, we're not trying to get to moles of CO2. You guys actually want to get grams of the sodium hydrogen carbonate over here. So let's go into our second step. If you look back here, it says our second step is to do stoichiometry, and remember to go to grams or moles of B. So let's take a look at what we're starting with. I'm going to be starting with 0.23461 moles of CO2 as my A. Okay, now, if I'm already at moles, you do not need to use molar mass, right? We could skip a step. You already have the moles, so now we could go straight to the mole-to-mole switch. So this is where I'm at. How many moles of CO2 do I have in my equation? It's a simple 1. I have 1 mole of the sodium bicarbonate, so it's a 1-to-1 ratio, pretty simple. And let's look to see what we're solving for. It says go to the mass of hydrogen, sodium carbonate, sodium hydrogen carbonate. So we're going to put 1 mole of NaH, CO3, And then we want to take this to grams of NaHCO3. My pen